Okay, Bismillahirrahmanirrahim. So for today we have Sir Abdurrahman and Sir Noor's topics. And first I'd like to start with this barrage design because it is the longest one. The other Sir Noor's problems are quite easy as compared to this. This barrage wood example, which we have already done in this lab portion. Sir said that this may come in parts. It cannot come because this is too long in whole, so it may come some parts of this problem may come. So we'll start from this. All right. So this is the given data. We are given the maximum discharge for which we have to design our barrage, the minimum discharge, river bed level, highest flood level, lowest water level, and minimum pond level. So if I draw this, so this is before construction of barrage. So this is our natural surface level. The elevation of this natural surface level would be our RBL, that is our river bed level. So this is 382, 582 feet. Sorry. So we have river bed level at 582 feet. Now they are saying that the highest flood level would be at 600 feet. So the water capacity like this would be elevation would be 600 feet, highest flood level. And again, the lowest water level would be 587. The minimum pond level. Pond level is after creation of dredge. So some of the water is stored on the upstream side. So this would be our ponding. So our pond level would be minimum 598 feet. They are saying that if this is our river in plan view and we have constructed a barrage like this. So there are two canals on right bank and one canal on left bank. So if this is a direction of water flow, so we have two canals on right side and a single canal on left side. And the slope of the river is 1 foot per mile, and the maximum discharge of the canal is 3500 cubics. So this is our all given data. First of all, what we have to do after we are given this data, first we have to determine the dimensions of the barrage. So first we have to determine what would be its length, what would be its width, and how many pairs in it would be, how many pairs would be, so all that. So first of all, we have to determine these dimensions. So for that, we are given simple formula that is pw is equal to 2.67 under Q max, and this is for FPS units. So this is Lace's formula for vector perimeter, that is 2.67 under Q max. Q max is 500,000 Q6. So if we write this 2.67 500,000, so we'll get some answer that is 1890 feet. 1890 feet. So this is minimum stable verted perimeter. This is minimum perimeter. So what we have to do is we have to multiply it by coefficient called Lace's lossless coefficient. It depends. This coefficient depends on the type of the plane or the topography of where the barrage is constructed. So if we have a plain area, it would be around 1.8. If we have a hilly area, we will use it as 1.1. So depending on the type of uh, topography given in the question, where we are construction of barrage, so we'll use this coefficient correspondingly. So our width of barrage or width between abutments would be 1890 times 1.8. We are considering it as a plain area. So if you multiply this, we'll get 3,400 feet. So if I draw this, so for example, this is our the side slopes of our river. So we are constructing a barrage here, like this. This we are constructing a barrage. So we are saying that its width, this is its width, width between abutments, WA, would be 3,400 feet. So now we have to divide this width into bays and piers. Bays are Piers are simply foundations, or you can say sports for the barrage, while the distance between two sports is one way. So we are going to divide this. So we have first of all bays, piers, fish ladder, and divide walls. Divide walls we provide at the extreme edges, these blue ones, because we call this portion as undersluice portion and we decrease this depth. So we provide our divide wall here. So we suppose this that one bay would be of 60 feet, a pier would be of 7 feet, fish ladder would be of 26 feet, and one divide wall would be of 15 feet, and we are providing two divide walls, so that would be 30 feet. So now we have to determine how many bays and how many piers we are going to use. We know that total width we have available is 3,400, this one. So just 3,400, subtract this switch shutter and divide wall from it, 30 minus 26, and divided by number of the width of one pier and one bay, 60 plus 7. So if we divide this answer, we'll get something like 49 point something, 49.9 something. So we'll round it up to 50. So this is how we can get 50 bays, and piers would be one less than bay. So we'll get 29 piers, but there are two revolve walls as well. So we'll get 47 piers. 50 minus 3, or just subtract 3 from the number of bays, we'll get number of piers. So this is how we can get the total number of bays and piers and all that. So the actual width of between abutments would be 50 times 60. That would be around 3,000. 47 into 7, 329, and 26 and 30. So if we'll add this, we'll get 3,385 feet. So this is, would be our width between abutments. And we have to calculate discharge also. So here we'll get Q abutment. That this is discharge per unit width between the abutments. So this would be 500,000. As we know that discharge per unit width is Q over B. So here the B value would be total 3,385. What we calculated here. So we'll divide it by and we'll get 147.7 CFS per foot. And the discharge in this portion where the weir is constructed or barrage is constructed, we'll call it a Q weir, and this would be a Q, the same discharge over, but here the look water area for passing of water is lesser, because these piers would block the water, this fish shelter would block the water, these divide walls would block the water. So the water can only pass to this 3,000 feet, only the base. So we'll divide by 3,000 and we'll get higher value of recharge, that would be 167.7 CFS per foot. So this would be our first step for design of barrage. First, we calculated the minimum vectored perimeter from Lace's formula. Then we multiplied by the Lace's lossless coefficient depending upon the topography where the barrage is constructed. Then we determined the number of pays, number of piers, and calculated the actual width between abutments for the branch. And using this width and the previous width, we calculated the discharge between abutments and the discharge between under the weir. So this step is fine. Is this step fine? This is the first step. This one. Should we move onwards?
Yes, brother.
All right. So Lace's self factor. The second step is we have to determine calculate the Lace's self factor. It has simple formula S is equal to 1 over 1844 F power 5 by 3 over Q power 1 by 6. So we know that S is here in the given data. The slope of the river is 1 feet per mile. So we can write S as 1 over 5280. As we know that there are 5280 feet in 1 mile. 1 over 1844 is the coefficient. This is for FPS units again. F43 we have to calculate, and Q we know that 500,000 or 1 by 6. So if we simply solve this, we'll get F value round about almost 1.99. So we can round off to 2. So we'll get the latest self factor as 2 from this equation. So after calculating this, the third step is we have to fix the crest level. The crest level of barrage. So if I draw the diagram, for example, this is our natural surface level or river bed level. We have constructed a barrage like this. On this, we are assuming that its height, the height of the weir or barrage, we can write as P, and this is 6 feet. We are just assuming this value. So above this is our supposed water level. So above the weir, this is the weir, this is a weir. So above the weir, this head, we'll call this water head as H naught. This is capital H and capital naught. So we'll call the head above the crest as H naught. And for example, this is our hydraulic rate line, and this yellow line is our energy line. So above this is our velocity at V naught square over 2g, and this is energy level above this V crest. And the total or the specific energy above the V crest, we'll call it as E naught. That would be, we can write the V naught velocity at H naught, small h naught. So the E naught would be capital H naught plus small h naught. The capital H naught is the water head, and the small h naught is the velocity head above the V crest. E naught is the specific energy above the V crest. Similarly, we can write this as this one. We know that this is the highest flood level. The highest flood level was 600 feet without the barrage. So if we have this is 600 feet, and we know that river bed level is 582 feet. So this normal depth of flow would be T naught. We'll call this at D naught. That would be 600 minus 580 naught, 582. So that would be 18 feet. But due to construction of barrage, what would happen that there would be some damming action upstream of the barrage. For example, the blue line was the normal flow of the barrage. This green line shows the damming action. So this damming action would cause some rise in the upstream level. We'll call this as efflux. This is efflux. We do not know this value, so we'll have to assume this. And again, this velocity head is the same. E naught square over 2g, again the H naught. We are considering that there is no losses between section 1 and section 2. This is section 1 and this is section 2. So we are considering there are no losses between these two sections, and this is the total profile of the barrage. All right. So if we understand this one, so we can write as height of barrage or weir is 6 feet, that we have written as P, and this total depth, this one, we can write this as R. R is the scour depth, because due to water flowing, some scouring will occur. So we'll write this as cover depth, and we can calculate it by a simple formula. Cover depth is equal to 0.9 times Q abutment square over F. So this is silt factor and the whole cube root. So if we put in the values Q abutment, we have this one 147.7, and laces silk factor we have 2. So if we plug in the values, we'll get this value about 119.9, 19.96 feet. So we know this R value, we know this P value. So we can calculate this H value, this H naught value. How? Simply subtracting R from P. This H naught would be, this is head above the VA crest, R minus P. So we have R as 19.96, P as 6 feet, so we'll get 13.96 feet. Simply, if we understand this, we can easily write these values. R, we know this cover depth. P, we have assumed the weir height. Simply subtract them and we'll get this H naught value. H naught is the head above the VA crest. And for V naught, we know that V naught is Q abutment over R. Suppose R is above this hydraulic grade line. V is here. V naught is here. So Q abutment we have 147.7. R we have as 19.96. If we divide them, we'll get the V naught value, that would be 7.4 feet per second. So we can calculate velocity at, this is small h naught, V naught square over 2j, V naught 7.4 square over 2 into 32.2, because we are using these FPS units. So we'll get this velocity at above the VA crest as 0.85 feet. Now if we look at this picture, the specific energy above the VA crest, E naught is the specific energy above the VA crest. This is H naught plus H naught, capital H naught plus small h naught. So E naught is equal to capital H naught plus small h naught. We calculate both these values. This is 13.96 plus 0.85. That would be 14.8. Alright. So this is how we can calculate this E naught value, the specific energy above the VA crest. Any issue up till this part? How we have calculated this E naught value? No. So after calculating this E naught value, we have to determine the energy level upstream of the weir. So if I draw this again, so if this is a weir, so we have to determine these energy values. This is efflux, this is D naught, and this is small h naught or V naught square over 2j. And this whole thing is E1, the specific energy upstream of crest level. So simply we can write this E1 as D naught, the normal depth before construction of barrage, the flux value, so flux plus H naught or V naught square over 2G. So now we have to assume this flux value. This value we have to assume. We have to hit and trial this value because if up in the end we'll check for this value if the our discharge would come very larger or very much lesser than the original discharge, then we have to divide this flux value. So this value we have to assume. For example, we are assuming this value as suppose 2 feet. So D naught we have 18 feet, flux we have 2 feet, H naught we have 0.85 feet. So we'll get this E1 value like this, 20.85. This is energy level upstream of the weir crest. Now, if you want to determine this total energy upstream of weir crest, this total energy upstream of weir crest, we can call it upstream energy level. So that would be E1 plus river bed level. So if we simply add E1 with the river bed level, we'll get this upstream energy level. So upstream energy level is equal to E1 plus RBL. We know up till this portion, this is RBL, and above it, this is E1. So simply if we add them, we'll get this upstream energy level. So E1 we have 20.85. This is we have 582. So if we add them, we'll get approximately 602.85. So this is our upstream energy level. Now finally, what we were going to, what this step was, we have to determine the crest level. So crest level, we can find this as this E1 total energy at this upstream level minus this E naught, that is specific energy above weir crest. So if we subtract this E naught from upstream energy level, we'll get this value. So this is our crest level of weir. That from a specific datum, we'll get how much height of the weir would be. So our crest level would be upstream energy level minus this E naught. So upstream energy level we have 602.85 minus 14.81. If we subtract them, we'll get our crest level 589.04 feet. All right. So this is how we can find the crest level. If I repeat this by simply drawing a diagram. First, we have decided some height of the weir. We'll call this as P. Now we know this scour depth. We calculate this scour depth from the formula, and we'll call this as R. So we'll subtract this R from P. We'll get this value H naught, head or water level above the weir crest. After getting this H naught, we'll calculate V naught. V naught would be simple Q abutment over R. So we'll get small h naught as V naught square over 2G, or velocity at above the weir crest. So this would be our small h naught. If we add them both, we'll get E naught or specific energy above weir crest, that would be H naught plus H naught. Alright, so this will get the specific energy above the weir crest. Now for upstream side, we'll calculate its specific energy by similar method. First, we'll get this normal depth of flow. We'll get this T naught by subtracting highest flood level and river bed level. If we subtract them, we'll get this normal depth flow. In this normal depth flow, we'll add some efflux value because there will be some damming action. We'll add some efflux value. This value we would assume ourselves because we do not know this value, so we'll have to assume this value. After adding this efflux value, we'll calculate this E1 value, the specific energy upstream of weir, as d naught plus a flux plus small h naught or velocity at. We'll calculate this E naught as like this. After E1 like this. After calculating this E1, we'll calculate total energy at upstream. That would be upstream energy level. That would simply be E1 plus river bed level. Up this river, we'll add this river bed level. In this E1, we'll get total energy upstream. Now, if we subtract this total energy upstream, this E naught from this total energy upstream, so we'll get crest level. That would be upstream energy level minus E naught. So any issue in this, how we have to calculate this crest level? Or should we move onwards?
Yes, brother, we'll go to the next one.
All right. So after this calculation of crest level, now we have to check this whether our crest level is correct or not, because we assume this flux value ourselves. So now we have to check this whether it's correct or not. So for that, first we have to check. Go to this rating curve. This rating curve. We know our discharge value as 500,000. So this is zero point 0.5 million, and we'll calculate or we'll get this normal depth of flow without the construction of weir. So this value of downstream water level, this would be without the construction of weir. So simply for our given discharge point of 4.5 millions, we'll get this value for normal state. We are currently doing everything for normal state. In the next steps, we'll do for retrogress and accreted states also. For this step, downstream water level we calculate from the stating curve. So that is about 600 feet. This is about 600 feet. So after this downstream water level, now we have to determine the weir submergence. We'll denote it by H. Weir submergence is how much the weir is submerged. For example, this is our barrage and this is water level. So for example, this is our hydraulic jump. So this is our crest level and this is our downstream water level. So the difference of these two, H is equal to downstream water level minus crest level. So the difference of these two would give us the how much is the weir submerged. That how much is the water level on the downstream side above the weir crest level. Simply the weir submergence H would be downstream water level minus crest level. So 600 minus 589.04. So we'll get this uh, weir submergence. So now if we go to this graph, this Gibson's curve. So for in this Gibson's curve, they in the y-axis we are given as H over E naught. So we have to calculate this H over E naught. We have calculated this H. So H over E naught would be, this is approximately 10.96 divided by E naught. We calculated E naught before. The specific energy above the weir crest. That was 14.81. So simply divide it by 14.81. We'll get some value, and approximately that value is 0.74. So now we have to go through this graph for this 0.74 value, draw this horizontal line, and it's made it as like this. So approximately this is 0.85. On y-axis we have, so on x-axis we have c dash over c value. So our c dash over c value would be 0.85 approximately. Now we know that this this c value, this c value we have to remember this is 3.8 for fps units. For fps this is 3.8, approximately 2.02 for SI units. But for we have to only remember for fps, so it would be at 3.8. So our c dash value would be c into 0.85 or 3.8 into 0.85 So that would be approximately 3.23. So now we have determined the C dash value. The discharge formula, we should know that that is C dash L H power 3 by 2. This is a typical discharge formula. In our case, this C dash value is 3.23. This L is actually the width between abutments. The length of barrage, if I show this, if you see this picture, so the length of barrage, this is the length of barrage. The length of barrage is actually the width between abutments. So simply we can write this as width between abutments or 3000 feet. Why we are using this 3000 feet? Because we are going to uh, design separately for the main weir as well as the undersluices. If you look at this, that after this step we have to design the undersluices separately. So we are designing this main weir separately. So we are using this 3000 here. For undersluices we'll use that 600 feet. So for 3000 feet time, and here we have H as E naught, the head above the VA crest. So we have this as E naught. So 14.81 raised to power 3 by 2. So if we calculate this value, we'll get this value as 552,276 cubic feet per second. So this is our discharge value. We assume the given discharge was 500,000. We calculated is 552,000. So approximately 10% above. This is fine. So we have a limit of approximately 10% on the above side. This is all right. So we are discharge about 5500. So we can say that this is okay, fine. But if we have to be more accurate, we can do this whole procedure again and bus by revising this efflux value. This efflux value, we assume this has 2 feet. So if we assume this has 1.9 or 1.8 feet, our discharge value would be reduced. So this is how, if we assume a wrong value of flux in the start, we'll get our answer here. That for example, we assume a 5 feet of flux. So our discharge here may be around 7,000 cubics. So that is much more than the given. So that was wrong. So we have to revise this value. But for approximately 10%, we can say this is fine. No need to revise this value. Okay. So this is how we can calculate the discharge value. Any issue up till this part?
No, brother.
All right. So the fourth step is design of undersluices. So this is very much similar to the before one. Just a little bit of difference is there. But if I draw this diagram again, this is our weir and this is our flow value. So for undersluices, we are assuming the crest level of undersluices is 3 feet below the original crest level. So the crest level of weir minus 3 feet. We are assuming this ourselves. So our crest level weir was 589 feet. So 589.04 minus 3 is 586.04 feet. So now we have determined this crest value. So just the difference would be like this, that we know this crest value of undersluices. And what we have to determine that this is pose energy line. We have to determine this upstream energy value, upstream energy level, and simply if we subtract them, we'll get this H naught and H small h naught values. So, or we can write this as simply E naught. So we have to determine E naught. Why we have to determine E naught? Because in this graph, this Gibson's curve, this E naught value we have to use. H over E naught value we have to use. So we have to determine this E naught value. And for this E naught value, we know the stress level in the case of undersluices. Just we have to determine is this upstream energy value, energy level, and if we subtract them both, we'll get this E naught value or specific energy above the VA crest. So for upstream energy level, so if we again divide this, this is V naught square over 2G or simple small h naught. For example, this was original flow level. So this is normal depth of flow D naught, and this is some efflux value. So and this is river bed level. So for upstream energy level, but we can write this as this is river bed level. This bottom portion, we have to add this D naught value in this normal depth of flow, and this efflux value in this efflux, and this velocity at small h naught. Now we know this D naught value as 18 feet. This would remain same because the normal depth would remain same. This river bed level we also know this has 582 feet. This reflex value we have to assume, for example, we assume 2 feet in the previous portion. Again we can assume 2 feet. So the only problem is this h naught value. And we know this h naught value is v naught square over 2g. So we know this g value. So v naught value would be our q abutment over r. So simply if we calculate this r value, so our r value would be 0.9 times q abutment square over glacis sill factor cube root. Now in case of this q abutment for undersluices, we'll use this q abutment as 1.2 times q. We are assuming that 20% more water is passing through undersluices because the undersluice portion is lowered by 3 feet. We have automatically assumed this crest level is below 3 feet. So we are lowering the portion of undersluices. So more water would pass through these undersluices. So we'll assume that approximately 20% more water would pass through these undersluices. So Q undersluices, we can calculate this as 1.2 times Q abutment. We know that 1.2 times what was abutment 166.7. So that would be around 200 CFS per foot. So this is undersluice discharge value. Now simply we can calculate this R value, that is 0.9 times 200 square over 2 cube root, and simply we can get this value as 24.43 feet. After this getting this R value, we can calculate this V naught value, that would be as 200 over, again we have to going to use Q undersluices over here, not abutment, sorry, undersluices over here, over 24.43. So this way we can get this V naught value, that would be 8.2 CFS, sorry, FPS, feet per second. And using this V naught value, we can calculate this velocity head. So V naught square over 2G, simply this is 1.04 feet. So now we can get this upstream energy level. Upstream energy level is river bed level plus D naught plus Flux plus H naught. River bed level is 582, D naught 18, Flux 2 feet, and H naught we calculated just before 1.04 feet. So this way we can calculate this upstream energy level, that is 602.84 feet. So this is our upstream energy level. Now for simply E naught, what we can do, simply subtract this upstream energy level and this crest level of undersluices. So E naught is upstream energy level minus crest level of undersluice portion. So 602.84 minus this crest level was 586. So if we simply subtract them, we'll get this E naught value. So approximately it was 18 feet. So this is had specific energy above the VA crest for under sluice portion. Now again we have to check, apply the check. So for the check, first we have to calculate the VA submergence, that is downstream water level minus uh, crest level. This downstream water level, this VA submergence is downstream water level minus this crest level of weir. So downstream water level, we can get this as your crest level of undersluice portion. Okay, so we know this upstream energy level is 602.84 feet. So simply 602.84 minus how much we lowered the weir crest. For undersluice portion, remember we lowered the weir crest by 3 feet. So simply subtract this 3 from this upstream water level. We are assuming there are no losses. So simply the upstream energy level minus how much we lower the undersluice portion. So this is downstream water level minus crest level is approximately 586. So we can get this as 15 feet approximately. Now again the same portion H over E naught we have to calculate it. This is modular ratio. This is called modular ratio H over E naught. So it H is we have 15 and E naught we have 18 feet. So simply divide them, we'll get this H of E naught value, that is 0.83. Now go to this graph. For 0.83 value, we get approximately this one value. I think this line is not straight. This one, this is like, yes. So for 0.83 value, we'll get C dash over C as 0.75 from Gibson's curve. Again, we have to use the same formula for Q under sluices, that is C dash into width of under sluices into E naught power 3 by 2. So C dash is simply 0.75 into 3.8. 0.75 into 3.8. C dash over C into C. Width of under sluices, we have two under sluices on both sides because we were given that canals are on both sides. So the 300 feet width was on one side, so 600 feet is the total width of under sluices. And E naught value we just calculated before, 18 feet, 18 power 3 by 2. So this way we can calculate discharge of under sluices, 132,000 CFS approximately. Again, the discharge of under weir portion, that would be C dash into width of weir into E naught power 3 by 2. Now for this C dash, we use the previous one that we calculated for the weir portion. So for weir portion, we calculate C dash as 3.23. So we'll use this 3.23 times width of weir is 3000 minus 600. We are subtracting this under sluice portion width times this E naught value we have as 14.81, the previous one, not the under sluice one, the previous one for width for weir. So we can simple multiply them and the answer is about 405 CFS cubic feet. Now if we add them, Q is equal to Q under sluice plus Q weir, so we'll get our answer as 537 CFS. So this is less than or approximately equal to 1.1 times Q. So that is 550,000. So this is our okay. So this design are this, the design of understood portion and the weird portion we are done is okay. So any issue in this? Should we move onwards?
Yes, brother.
Right. So after this steps, now we have to check our wear for different discharge values, because for all the cases, it's not like that always the highest flood level will be passing through the weir. Different values of discharge will be passing. So we have to check our weir for all the different values for critical cases. So for that purpose, we'll draw this table like this. So the step 5 is we have to check. So for this step, first we have to determine the discharge values, the Q values. So for critical cases, we'll assume as 1.2 times Q, 1 time Q, half Q, and quarter of Q. So 1.2 times Q is 600,000. This is 1 Q is 500,000. Zero point 0.5 is 250,000, and 0.25 is 125,000. So these are discharge values. We have to check our wear against all these values. So for this discharge values, first of all, we have to determine the downstream water level. How we can determine this downstream water level? From rating curve. Rating curve. So if we go to this portion, this rating curve. So for six, yes, and we have to do this for normal state, for retrograde state, and for accreted state. Same, we have to perform this step for all these three states. For example, if we do this for retrograde state, we did the one before for normal state. Now, for example, we are doing this for retrograde state. So for 600,000 feet, cubic feet per second, in retrograde state, our head would be, the downstream water level would be 595 feet. This one, this curve. So for 500,000, this would be 595 feet. For 1Q or 500,000 feet, this is approximately again 595. For 250,000, so we can write this as like this. So approximately it is 590 feet. And similarly for 1 to 5, we can determine this as 582.5. Like this, we can calculate the downstream water level for all these cases. Now we have to find this actually this upstream water level. If I draw this again, this is our weir, this is our downstream water level, and we are assuming that this downstream water level plus this flux value, this would be upstream water level. So the downstream water level plus this flux value would give us this upstream water level. So now for second step, we have to assume this flux value. So for example, we are assuming this flux value for this as 5 feet. For retrograde state, the flux value would be higher. The upstream water level would be simply downstream water level plus a flux. This thing. Upstream water level is downstream water level plus a flux. So simply 595 plus 5, this is 600 feet. After this upstream water level, we can calculate this upstream depth. This is the upstream depth. Upstream, we can call this as D, upstream depth. So the upstream depth is simply this upstream water level minus this downstream water level. So for example, this upstream depth is, sorry, this is upstream depth. So upstream water level minus downstream water level. So this would give us this upstream depth. So, sorry. So our upstream depth would be this upstream water level. This is upstream water level minus this river bed level. This is our river bed level, RBL. So if we subtract this upstream water level from this river bed level, we'll get this red value. So this is the upstream depth. not this one. This is head loss. So upstream depth would be upstream water level minus river bed level. So upstream water level is 600 feet, river bed level is 582 feet. We'll get this upstream depth as 18 feet. So after this, we can calculate the Q here. Simply, this is Q over A. Sorry, Q over B. So we have Q here as 600,000 and B as 3,000 feet. So we can calculate this as 166.7. All right. The same procedure we are following, just we are doing this for a lot number of values. Before we are doing this for one value, now we have to do this for this value as well, this value as well, this value as well, and for the normal state as well as accreted state. We are doing for retrograde states only. So after this Q here, we can calculate the V naught or the approach velocity, that would be Q here divided by upstream depth D. So if we divide this Q here over V D, we'll get this upstream depth. So our Q here was 166.7 divided by upstream depth, that is 18 feet. So we can divide this and we'll get this upstream depth. Okay, one there was a mistake that here we have to use not this 3000 value. We are because using this for wear only, so we'll have to divide this value by 3000. Okay, okay, it was fine. Sorry, this is 3000. It's okay. So we'll get this V naught value. After H naught, that would be our V naught square over 2G. Simply, we can get this head upstream, what this velocity head in the upstream side. H naught is equal to V naught square over 2G. So this is our velocity head on the upstream side. We can simply calculate this as V naught square over 2G. So we can get this V naught square over 2G. Now we know this total energy at the upstream side. We can calculate this H naught. How? We can simply subtract this upstream water level and this crest level. So if we subtract this upstream water level from this crest level, we can calculate the water height above the VA crest. So it would be upstream water level minus this crest level. So if we subtract them, we'll get this H naught. And after calculating this H naught and small h naught, why we are using this, doing this, because we wanted to find the specific energy above VA crest. That is small h naught plus capital H naught. So we can calculate this as E naught. After the C naught, we can find this H or VA submerges as downstream water level minus crest level. Simply subtract this downstream water level from this crest level. We can get this VA submerges. So we'll get this H value as VA submerges. After this H value, the same value the same procedure we have to follow. We have to find this H over E naught, C dash over C from the graph, and C dash value by multiplying the C dash over C by 3.8. And if we multiply the C dash with the width of weir, we'll get Q small q weir. And if we multiply the Q weir with the sorry, if we multiply the C dash with E naught raised to power 3 by 2, we'll get the small q weir. And if we multiply the small q weir with the width of weir, we'll get the total discharge passing through the weir. So if I show this Excel value, so just we have to assume this flux value. We have to find this upstream water level as downstream water level plus a flux. The upstream depth would be this upstream water level minus river bed level. The Q here we can calculate this simple discharge over width. We can calculate Q over upstream depth. H naught V naught square over 2G. H is our upstream width or height above the wave crest. E naught is our specific energy above the wave crest. Simple add H naught and H naught. H is the weir submergence. Simple subtract the downstream water level from the crest level. Then H over E naught, C dash over C, C E over C naught in Q we can calculate. Now the check is that the Q we calculated before the previous step should be near about the Q we calculated now. This would be about again about 10% difference is allowed. More than that, we have to revise this flux value. So if we most get this value as 250 CFS per foot, we have to change this flux value. We have to decrease this flux value. To decrease this Q here. But if they are both near to each other, then that's fine. So this is how we have to do this for main weir, and again we have to do this all for the under sluice portion. Just the difference would be that discharge we would assume as 1.2 times Q because we are assuming that 20% more discharge would be passing, and the Q weir we would assume as for this width of the weir we'll assume this as 600 feet for the width of the under sluice portion. Just only this difference would be there. The rest of the portion would be same. Any issue on this portion? This is very more calculation work, so most probably this would not come, or simply one value would come. More than this, or if we have to construct this whole table, then we cannot do anything more in the paper. Only this table would be constructed. Any issue in this?
No, Hamza.
All right. So after this, we have to design our flow level by Blanch method. So we have three methods for designing the floor. First is Blanch method, second is Crump's method, and third is this conjugate depth method. So we can design any using any method, and this is very much a short question because this is there are high chances of this coming because there are small questions and we have to use graphs to determine these values. So sir could give this part as a separate question. So we can design for any method using any method, and we can check using both from one method like Blanch method. We can check this flow level using the other two methods, Crump's and conjugate method. All right. So for first of all for Blanch method. So if we look into this Blanch curves, this is Blanch curves. These are Blanch curves. So if we look into these curves, in the these curves are of some specific discharges. Like this one, where my pointer is of 100 CFS. This one. This one is of 100 CFS. So this 110, 120, 130, 140, and so on. So we have some specific discharge values for these curves. On the y-axis, we have this head loss value, this HL. This is head loss value. This we have to calculate. And on the x-axis, we have this E naught, E2 value. This we have to see from this curves. So first, we have to know this discharge value. Then we have to calculate this HL value, head loss value. Using these two things, we can calculate this E2 value. and from the C2 value we can find the downstream flow level using Blanch method. So this is simple method. So for example, this is Blanch method. So first we have different Q values. So for example, we have Q values 1.2 Q, 1 Q, zero point 0.5 Q, zero point 0.4, 0.25 Q. So we can write this as Q. This is 1.2 Q, Q, 0.5 Q, 0.25 Q. Or simply this is 600,000, 500,000, 250, 250,000 and 125,000. So this are discharge values. Our discharge per unit width, this Q would be simple, Q over width of weir. So if we divide this Q value by width of weir is 3000 feet. So we can get the small Q value. So 600 divided by 3, this is 200 CFS per feet. Similarly, for this, all these values can be calculated. After this, we have to determine the upstream energy level and downstream energy level. Upstream energy level, downstream energy level. Now we have to get these values. If we look before, we determined this downstream water level, this one, and this upstream water level. If we simply add the velocity head into this downstream water level and downstream upstream water level, we can get the energy levels. If we look into this curve, so if what is this energy level? If this is downstream water level, so energy level would be this downstream energy level. Simply the addition of velocity head h naught, small h naught. If we add in water level, then velocity head will get the energy level. So our upstream energy level would be upstream water level plus H naught and downstream water level plus H naught. We calculated H naught before, we calculated upstream water level before this, and we calculated downstream water level before. So all these values are known to us. This is H naught. So simply we can use this value and calculate this upstream and downstream water level energy levels. Now what is head loss? Head loss is actually the difference of upstream and downstream energy levels. This thing. What I segment did before. This is actually head loss. This is upstream energy level minus downstream energy level. Simple, the subtraction of both energy levels, we can get this head loss HL. So HL would be upstream energy level minus downstream energy level. Simple, if we subtract them, we can get this HL value. Now after this getting HL value, we know this Q value, and we can use the curves, sorry, these Q values. We can use both these curves, both these values to get the value of E2. So for example, we have small q as 200 CFS, and we have HL, suppose we have HL of 17 feet, assuming we have a 17 feet HL. So we have to use this 200 CFS curve, this one, move downwards until we are on 17 feet. Sorry, we have this HL value as 2 feet. The difference of downstream and upstream energy level will be small, not very large. Like this, we have upstream water level 600 and downstream water level 595, so we can write this approximately 5 feet. So we have 5 feet of head loss. So for 200 CFS curve, if we move downwards, so for 5, we have to check on the y-axis. So at this portion, I think, at this portion, our head loss value is 4. So for example, at this portion, we have a head loss value of 5. So approximately at this portion, this value. So this is a little bit more than 19. So we can write this as approximately 19.1 feet. So our E2 value is 19.1 feet. So this is how we can use the curves to get this E2 value. And simply the downstream flow level would be downstream energy level minus E2. Simply this downstream energy level, if we subtract E2 from this, we can get downstream flow level. This is actually, if I draw this, so this is downstream energy level. If we subtract from this downstream energy level this E2, E2 is the specific energy downstream of the weir. So if we subtract this from this, we can get this downstream flow level. This downstream flow level we can get. So this downstream flow level we can get this value. By this way, we have to do this for all these portions. The minimum value we would get from this tables. We have to use this. This was for normal case. We have to also we have to also do this for retrograde state as well as accreted state. For all these states, we have to do this. And the minimum value of the downstream flow level we have to use. All right, and afterwards we have to use this. We have to do the same procedure for undersluice portion as well, like this. So they are calculated this retrograde state like this, and accreted state like this, and this is for our undersluice portion. So we have to do this for all these portions. So any issue in this, how to check from Blanch curves?
No issues, brother.
All right. So after Blanch, the second method is crump. So for crump method, if we move to its graph, this is crump's graph. So if we check this, we have to find this K plus F4C value. We have to determine this K plus F4C value. If we can, how we can get this value? We have to know this HL over C. This is HL over C. Head loss over critical depth. C is the critical depth that we did in the previous course of hydraulic engineering. So this on x-axis we have HL over C. For any value of HL over C, we have to calculate. We have to move to this K plus F over C curve, and we have to check the value on this y-axis, and we have to see this left portion values. These values, not these values. These are for, sorry, we have to check these values on the right side, these values, not these values. These are for y over c. We do not need this. We also only need this k plus f over c value. So we have to check this value on the right hand side. So for example, this is, we can write it as 7.5 approximately. So for Crump's approach, what we need this k value, we need this f value, we need this c value, or we need this head loss and we need this c value. So again, we have to calculate this head loss similarly like before, but we can calculate c value. We know that what is the critical depth, yc is equal to q square over g whole power 1 by 3. So for one value of discharge, for example, we have discharge of 500,000 CFS. First, we have to reduce the discharge. For we are doing this for example, this is our discharge. Now we have to find this downstream water level, like we calculated before. For example, in these tables, we have calculated this downstream water levels. These values. So we have determined this downstream water level. We know these values. So we know this downstream water level. We have to pick the maximum one and we have to pick the minimum one from these tables. These tables. Maximum one, for example, we have as 604. Minimum one we have as 591. Oh, sorry, for 5,000 feet cubic feet, we have maximum as 602 and minimum as 596 for 500,000 cubic feet. 602.5 and 596. 596. So we have determined this downstream water level. Again, the upstream water level. Simply pick the values from this table. Upstream water level is for maximum is 604, for minimum is 601. 604, 601. After calculating this downstream water level, now what we have to do, you have to calculate this downstream energy level. Upstream energy level. Upstream energy level. So upstream energy level simply would be upstream water level plus H naught, the velocity at. Again, we know the value of H naught. We have calculated this. So simply add the values upstream water level with the upstream with the velocity at. We can get this upstream water energy level. After getting this upstream energy level, we have to calculate downstream energy level. So like this, in Blanche method, what we did, we calculate upstream energy level, we calculate downstream energy level, we subtracted them both and to calculate head loss. In same way, we calculate the upstream energy level. Just the difference in this method is the downstream energy level. We would not use this formula downstream water level plus H naught. Actually, we have to calculate downstream energy level in its own way. Then we have to subtract them both to get this head loss, and we can get this E2 values again. So after that, downstream water level we can calculate as Q over A, and we have Q as 5,000 feet cubic feet, and A we have as downstream water level. We can call this as D pool. That this is D pool is the downstream water level pool, downstream water level times uh, the width at the downstream side. So that would be width of abutments because there is no weir in the downstream side. So the width of abutment. So D pool simply would be downstream water level minus downstream flow level. So simply this downstream water level that we have calculated before, this downstream water level, this one that we have calculated before, that we have also written here. We have to subtract the flow level from this, and the flow level we have calculated from the from the Blanche method. From Blanche method, it was approximately 576 downstream flow level. We calculated from this. We are now checking this flow level. So simply subtract them. We can and get downstream pool level at downstream. So after that, we can get the downstream velocity as Q over A. This is downstream velocity actually. So this is Q over D pool into width of abutment. Width of abutment was approximately 3385, I think. So we'll use full width, not 3000. We'll use the full width because it is a downstream side. So after calculating this downstream velocity, we can calculate downstream energy level. That is simply V naught square over 2G. Simply square and divide by 2G. This is downstream energy, downstream velocity head. And for downstream energy level, simply add downstream water level plus H naught. We at the water level with the H naught, we can get this downstream energy level. Now, after finally doing all this thing, what we can, what we have found out, if we look at this graph, we have calculated this upstream energy level. We have calculated this downstream energy level. Now we have to calculate this K value. K value is the width of water of the weir crest. So how we can calculate this K value? Simple. If we subtract the upstream energy level and crest level, we can get this K value. So simply after this portion, K value would be upstream energy level minus crest level. This crest level. So we can get this up K value. And head loss, the head loss would be upstream energy level minus downstream energy level. This thing H1, this is HL. So HL or L would be upstream energy level. We are writing here head loss as simply L. Upstream energy level minus downstream energy level. Sorry, energy level. Simply subtract them, we'll get this upstream head loss value. All right. So C value we can get as Q square over G whole power 1 by 3. So we can divide L by C, and now we have got the denominator in, the x-axis value for this method. For example, our L value was about 2. L over C values was about 2. So for about 2 value, this 2 value we have to move to this curve, go horizontally, and our K plus F over C value would be 4. You can write as 4.5, I think. So K plus F over C value we have written as 4.5 from graph. For now, we can get this S value. We know this K value as this portion, suppose this was 17 feet plus F, or suppose this C value was 9 feet. So 4.5. Simply rearranging this part, we can get this F. This is F is the depth of hydraulic jump. This is F the depth of hydraulic jump from the crest level. After this, getting this F value, we can find the position of hydraulic jump. Position of hydraulic jump would be simply this F value, this crest level, this is crest level minus this F value. You can get the position of hydraulic jump. Crest level minus this F value. If we subtract them, we can get this value. Now after this, we have to find the E2 value, like in the previous part. So the E2 value would be downstream energy level minus hydraulic jump. So for example, this is downstream water level. So if we subtract the downstream water level and this E2 value, hydraulic jump value, we can get the E2 value. So if I write this as E2 is equal to downstream energy level. This is the downstream energy level. This one minus this position of hydraulic jump. This is hydraulic jump, and this is E2. So downstream minus hydraulic jump. So if we subtract them, we can get this E2 value. And jump submergence, just like before. So jump submergence would be hydraulic jump minus downstream floor level. So we have to calculate how much is the jump submerged. This jump, hydraulic jump minus downstream floor level. Subtract them and just get this value. All right, so we have to remember these steps. After this jump submergence, we have to calculate this length of glacis. This length of glacis. So we are assuming that slope is 3:1. That 3 is horizontal, 1 is vertical. So the length of glacis would be 3 times this value, this total value. So if we this is the jump submergence. If we multiply this jump submergence with the 3, we'll get this length of downstream glacis. So into jump submergence. So simply multiply this value with 3. We are assuming the downstream sloping is 3. After this, we have to calculate the length of stilling pool. This is simply 4.5 times E2. Simply what value was E2 was calculated, simply multiply it by 4.5, we'll get this. And finally, the length of downstream floor, that would be 4.5 E2 minus 3 into jump submergence. So simply subtract the top value from 4.5 E2, we can get the length of downstream floor. This is how we can calculate the downstream floor length from the uh, Crump's approach. In Blanch's method, we can only get the downstream floor level. We cannot calculate its length, but in this method, we can also calculate its length. So this is how we can calculate its length. Any issue in this?
No, Hamza.
All right. The last method is conjugate depth. So this is simpler method that we do not have to use any graph for this method. This is simple method. So for this uh, method, first we have to calculate this e value. This one. For example, if we have written this q value as 500,000 CFS, first we have to assume that only 80% discharge is passing through this portion. We are designing separately for weir and for understool portion in this method. So 0.8 of Q, we have to assume this. So this would be about 400,000 CFS. We are assuming that 80% discharge is passing through this main weir portion. So for this discharge, we have to get this upstream what energy level. So we have to get this maximum and minimum. We have to design for both maximum and minimum. So for upstream energy level, again we have to move to this graph, and here we have this upstream energy level. This is upstream water level. If we simply add this H naught in it, so we'll get this upstream energy level. So simply add upstream water level plus this H naught, small H naught. So we'll get this upstream energy level. After this upstream energy level, you have to calculate this discharge. Q is equal to Q over width of weir. In this case, remember this Q is, we have Q of 400,000 and this width of weir is 2400. We are subtracting 600 from this. We are not considering the understood in this portion. So we are only using the width of main weir only. So width of weir. So using this Q value, we can calculate the downstream water level. Downstream water level is we have as, suppose we have downstream water level as 600 feet or anything, we can assume. We have already calculated this one. So after doing this downstream, getting this downstream water level, depth of pool would be again same. That is downstream water level minus downstream flow level. That this is if we have this here. So this is our uh, water level. So this is downstream water level. If we subtract this from downstream flow level, say downstream flow level, we'll get this depth of pool, D pool. This is D pool. So simply subtract them and we'll get this D pool value. Using this D pool value, we can calculate E naught power 3 by 2. E naught was simply this one. This we have already calculated. So we can simply use this E naught value and or we can simply calculate again. Simply E naught is upstream energy level minus downstream flow level. We can calculate again. So actually we have to calculate again. This is E actually. So upstream energy level minus downstream flow level. If we subtract them, we'll get this E. Simply E raised power 3 by 2. Why? Because in formula we have this thing. Fz is equal to Q over E power 3 by 2. So our function of z would be Q over E raised power 3 by 2. So for this fz value, for example, our fz value was approximately, we can say 1. Fz value was 1. So for fz value of 1, we have to go to this table and check for this fz value is 1. So for approximately this one, we can actually interpolate between the above and the below values, but uh, these values are very small, so we can simply pick the nearest one. So for x value approximately 1.0418, our z value and z bar values are this one. We have to pick for phi is equal to 1 values. For, for phi is equal to 1, z value and z bar values are 0.14 and 0.6275. 0.6275. Using these Z and Z bar values, we can calculate D1 and D2, the before and after jump depths, conjugate depths. That is simply E times Z and E times Z bar. This is before jump, this is after jump, the depth of water. So after calculating this, we have to check the jump submergence. Jump submergence is depth of pool minus D2. So if our depth of pool, this is our depth of pool, is greater than D2, then that's fine. If this value is positive, greater than 0, okay. That our jump is fully submerged, that is great. But if this value comes less than 0, we have to revise this because our jump submergence would not be achieved, so we have to revise this. Alright, any issue in this? This is comparatively simpler. So this was all the major question for um, uh, super surface flow or surface flow. After this, there are small portions like scour protection. These are simple formulas. We have to memorize them and we can simply use them. These are small formulas. We have to remember these. Only the difficult thing is this backwater curve, Bress's backwater curve. When we are designing these marginal bunts for our barrage, so this difficult portion is only this one. The other are simply formulas. So in this portion, we have these formulas. So D1, D2, S, D, and C. What are D1 and D2? We get to this in a minute. The S is the slope of the river. T is the and C is the chases coefficient. G is the gravitational acceleration. D1 phi into D1 over D and phi into D2 over D. These are functions. We can get these values from this. For D over D values, we can get this phi D over D values from this table. These are basis functions. So for this, if you move to this, we have upstream water level at north of Guayban as a moment. Yes. So we have this downstream highest flood level without where we can get this from dating curve, and this was this with accretion without. D is the normal depth flow. That is simply highest flood level minus river bed level. This highest flood level was 602.5, and subtract from this 52 will get this D normal depth of flow. D1 is the upstream depth highest flood level minus river bed level. The D1 is upstream side depth minus river bed level. So upstream highest flood level was 604 feet. Again, we are getting all these values from this table. This upstream water level we are getting from this value. So we'll get this upstream water level from this, and upstream highest flood level we get is 604. Subtract river bed level from it, we'll get this 22 feet. So we have calculated this T1 value, we have calculated this T values. So now if we look into this formula, we actually know D1 S D S C changes coefficient is known 71 G and phi D1 over D. For phi D1 over D, simply divide D1 divide by D. For example, D1 is 22, D is 20.5, our D1 over D was approximately this one, they have written 1.073. So for value of 1.073, move to these tables. So 1.07. So approximately here 1.07. We can interpolate them, or simply we can use this 1.06 value 0.8382. So 0.8382 they have, I think, interpolated. If they have interpolated, yes. So we can simply interpolate or simply use the nearest value because they are very small values. So for D1 and D values, we know this D1 and D values. So now if we go to here, we know this phi D1 over D value also. The only unknowns are D2 value and phi D2 or D values. Now for D2 value, we have to assume this. Assume D2 value. We have to assume this. Then we have to calculate D2 or D. Simply divide the D2 with D. And after dividing the D2 by D, we can get phi D over D for the D2 value. For example, they have assumed the D2 value as 21.87. 21.87. Divide this by D, we'll get this value. They use the phi for this as 0.8287. Now plug in this value in the equation. Plug in this value in this equation. So this length, the value of length, the value of length should be approximately same as we calculated in the previous step. We have not actually done the previous step, but if we move to the previous step, the length of we calculated was approximately 48,49,000 feet, 48,900 feet. This one, this length of guide banks, this was width of abutment times 1.5. Simply multiply the width of abutment, we have 3375, I think, times 1.5, we'll get this 5078. And our this length from this equation should be around this value. This 507, 52040 and 5078 are very near, so that's fine. So these values should be very near to each other. If they are not near, then we have to revise these D2 values, calculate again D2 or D, calculate phi D2 or D2, and D and calculate again this L value. So our L value should be near this D value. So only this difference, and this is only the problem here. The rest is same. The rest is simple. Simple, we have to use the value. The only difficult thing after this is uh, this table they have again drawn on the same basis. They assume this D1, D2 values and D value was from the curve. So using this table, they have calculated the length. So you can draw this in the table, but this table would not come. This is very lengthy procedure. So simply, if we know how to calculate this one step, single step, this is fine. Can come in a simple short question. Now, the major thing, difficult thing for the barrages is this was all for the surface flow. Now we are going for subsurface flow. Subsurface flow. So for subsurface flow, for example, if we have this barrage like this, we have installed some number of sheet piles. These are sheet pile. This is upstream sheet pile. This is intermediate. This is again intermediate. This is downstream sheet pile. For example, we have installed 4 sheet piles. Now we have to determine these sheet piles length and how much uplift pressure uh, they are going to sustain. So for the sheet pile length, simple for the upstream side, the length is simple 1.5 R, and for intermediate is 2 R, 2 R, and downstream is again 2 R, where R is the cover depth, we calculated in the first step. Simple 0.9 times Q abutment square over G, the cube root of this portion. So for upstream portion, this is 1.5 R. For intermediate portion, this is 2 R, and for the downstream portion, this is 2 R. This way, we can calculate the length of the sheet piles. Now we know here the upstream river bed level is 582. If we subtract this 1.5 R from this 582, we'll get the reduced level bottom of upstream sheet file. So we can get this as upstream sheet file as 574. This is 574. And again for others we have 40, 40. So subtract. Okay, we have to subtract this upstream water level from this. Not sorry, upstream bed level. We have to subtract this upstream water level. This this was 604 was the highest flood level for a created state. So for this we have to subtract this minus 1.5 R from this, and we'll get this 574. And for we have to subtract 2 R, we'll get 564, 564. And for downstream we have to assume some value. We'll check in the next step. We assume 550 value. So for downstream we have to assume 550 assume. Remember, for downstream we have to assume. This is how we can get the reduced level of the sheet piles. After this reduced level, we have to calculate the exit gradient. Exit gradient for downstream sheet pile. So for exit gradient, our formula is GE is equal to H over D 1 over pi and root lambda. This is H over D 1 over pi and root lambda. Alright, so H is the head, the differential head for seepage. The differential head causing seepage. So differential head causing seepage. So the critical case would be that the water level is fully on the upstream side, but there is no water level in the downstream side. There is no water level in the downstream side. So the water level at the upstream side is 604 feet. H is equal to 604 feet minus downstream bed level. So the downstream bed level is 576 feet. Now here we are assuming some retrogression of 4 feet. This is assuming this 4 value we have assumed ourselves. The way we are assuming that some retrogression may occur. So we are assuming as 4. We can take it from 2.5 to 8 feet. So we are assuming here 4. So this value is 32 feet. The d value, small d, the d value is the depth of downstream sheet pile. So if the downstream this flow level was 576, if we subtract the 576 from 550, the bottom of downstream sheet file, 576 was its top portion, 550 is its bottom portion. So 26 feet. This is our downstream sheet pile length. So we can get the downstream sheet pile length. Now we have to calculate the total length of concrete floor. So for total length of concrete floor in the previous portion, if you check, we have designed this as 50 feet upstream portion. The downstream bed was as 75 feet. We have designed this as upstream and downstream. Now we are assuming this stress level crash width is 6 feet. We are assuming it ourselves. There is no uh, issue. We are assuming this. We are assuming the upstream slope is 1:4. Downstream slope is 1:3. So these are slopes we assume. This crest level we assume. So this horizontal portion would be simple. We know this crest level is 589 approximately. Simply subtract 589 from 582. 589 from 582. This is the vertical ordinate multiplied by slope 4 will get this horizontal ordinate. In the same way, this we can calculate as 589 minus 576 downstream bed level times 3 because here the slope is 3. So this way we can calculate this value. So they have calculated this 50% is the upstream portion, 75% is the downstream portion, and 73.28 is the middle portion. This portion plus this portion plus this portion, add them and we can get this value. So this way we can get this values. This is total length of floor B. This is D and the B is 50 plus I think 73 something plus 75, that is something 198. So this way we can calculate B. Now alpha is equal to B over D. Simple divide B over D, we can get this alpha value, that is 7.64. Now if we move to the curve, this one. So if you move to this curve, we know this alpha value is 7.64. So for approximately 7.64, this one. So our value of this whole factor, this whole factor, this we can calculate from graph. So for value of 7.64, approximately this is 0.15. This curve we have to use alpha versus pi over 1 pi over lambda. So this is 0.15. So simple, we know this h value, we know this t value, we know this factor value. Simple multiply, we can calculate this GE value. So if we look from here, the GE value is 0.187, and this GE value should be between 105 to 107. 105 is 0.2 and 107 is 0.14. So it should be between these. If this is not between this, we have to revise this 550 value that we assume, this value. We have to revise this. If this value was more, we have to decrease this one. If it was less, we have to increase this one. All right. So this way we can calculate the sheet pile length and sheet piles downstream reduced level, bottom reduced levels. So afterwards, the only different step is this: that correction for uplift pressures. So for correction for uplift pressures, we have three different types of piles. First of all, we'll have to use for upstream piles. So we have to do the same step for downstream and intermediate piles for upstream piles. B1, B1 is the, for example, this is our branch. So this is our upstream pile. B1 is the width of concrete floor before the upstream pile. That before upstream pile, what is the width of concrete floor? So we have assumed this has 50 feet. B2 is the distance between the two piles. This is, for example, second pile. So they have taken this as 198.28. The before 198.28. The top and the first and the last pile. The B2 is 198.28. Or we can simply write as B. B is 198.28. And D is equal to, for this upstream pile, the D value is 582. This is 582 minus 574. River bed level minus the bottom of reduced level of bottom. 582 minus 574. So this is 8 feet. So this is 8 feet our depth of sheet pile. Now thickness of floor we have to assume, we can assume 2.5 feet. Simply pick these values from here. 2.5 here for this, middle they have used 10, again they have used 7. So simple, remember these values. Now after calculating this value, what we have to calculate, we have to calculate 1 over alpha, that is alpha was B over D. Alpha was B over D. So 1 over alpha would be D over B. So if we calculate this D over B, we'll get this value as 0.04. 0.04. Alpha would be 1 over 0.04, that would be 25. And B1 over B is 50 or 198.28. 50 or 198.28 is equal to something value 0.25, and 1 minus B1 over B is equal to 0.75. Just calculate these values. We are going to use these values for the graph, so just calculate this value. We have to remember this, we have to calculate all four values. Now we have to move to the graph. This one, this bigger one, this bottom one. So if you can see this, what have they written here? If 1 minute. So for example, if this is a sheet pile, what is the standard designation? That we call this point as C, the bottom one as D, and the top one as E. The C is the right one, the D is the bottom one, the E is the left one for the sheet pile. For any, for this standard, for the graph, standard designation is this. So they are saying to find phi E for any value, we have to read phi C for ratio 1 over B minus B. So we have to read phi C graph. This graph is for phi C, the left one. The right one is for phi D. They have written this. So for phi E, there is no graph given. But for they have said that for phi E value, we have to read this phi C value for ratio 1 over B minus B. So we have to read uh, the phi C value for this one, 1 minus B1 over B. And what we have to do again, subtract that answer from 100. So phi E, we can write this as phi E is equal to phi C. Phi C was for 1 minus B1 over B, 100 minus phi C. This thing. So 100 minus phi C. Phi C, we have 1 minus B1 over B as 0.75 and alpha is 25. So for if we move towards in the vertical direction, the alpha is 25 like this. So for example, like this. So if we move horizontally, so like this, 31, 32, 33. phi C value is 33 for B1, 1 minus B1 over B. Remember, this is for 1 minus B1 over B. So phi is 100 minus 33, that is 67%. Okay, so this is how we have to use the graph. The second value is phi D. We have calculated phi C. Sorry, we have calculated phi E. We have calculated, now we are going to calculate phi D. For phi D, see that the value of B1 or B, this horizontal is B1 or B, are more, all are more than zero point 0.5. So what we have to do in this case, to get phi D value of B1B less than zero point 0.5. Remember, our B1 of B was less than zero point 0.5, that is 0.25. For less than 0.25, uh, read for 1 minus B1 B and subtract 400. So if I write this as 100 minus phi D for 1 minus B1 over B. So 1 minus B1 over B is 0.75. Again this thing, and alpha value is 24. So again if you move this, so approximately 24 is this. If you move in this direction, so approximately 31, 32. We can write this as 31, 32. So 31 approximately. Oh sorry, 100 minus 31, that is 69%. So we can get, we got 67% phi D, phi E. So we got phi D as 69%. The last is phi C. Phi C is simpler, that we have values of all B1 or B. We have x-axis. So for B1 or B 0.25 and alpha value of 25, we can get this phi 61, 62, 63, 64, 65. So phi C value is 65 simply. Alright, any issue in this? This is how we have to use this course laws method. So they have calculated this phi B, phi A. They have just named this portion as A, K, and B, I think. So actually, this is E, D, and C. They have written this as B as D, yes, and I think just they have changed the naming. The rest is thing. The rest thing is same. So after this, only the thing we have to do is to apply the corrections. So for corrections, that thing is simpler. Just we have to remember the formula. There are three types of corrections. Just we have to know how to read the graph, because that is very important. For correction, for thickness of floor correction, this is TF, the thickness of floor that we assume, phi1 minus phi2 times T. So for this even correction, we are going to use thickness of floor as I think 2.5. Phi1 minus phi2 is phi E minus phi D, and D we already know. The depth of sheet pile. And we have to apply the correction in C part also. Look, they apply this correction in A part, that is I think E part, and the K part, that I think is the B part, the C part. So they applied correction in both portion. So simple subtract the uh, above what we have values obtained above, and multiply by TF by D. We get corrections. Now interference of sheet pile, this value we have this formula. In this formula, this is small d is the sheet pile upstream sheet pile length. The capital D is the downstream sheet pile length. B is again the thickness of floor 198.28. D is again the downstream sheet pile length. B dash is the thickness of floor before the upstream sheet, before the sheet pile. So for example, this is a sheet pile. Now we have the total upstream length as 50 plus 73. So we have 123 feet. B dash. Sorry. B dash is the distance between two sheet piles. So we have 73 feet. Simple. So we can calculate correction in K. The last correction we have to apply is the slope correction. So slope relation is Fs Bs over B. So Bs over B1. Bs is the sheet pile distance. Fs we can calculate from this different slopes. For upstream we have 1:3. The correction factor is this. For downstream we have 1:4. The correction factor is this or something, or this way we have for upstream or downstream. You can check. Just remember that negative for downward, negative for upward, and positive for downward slope. Positive for downward, negative for upward slope. Just remember this. And BS is the slope length. Again, like we calculated like this: 589 minus 582 into this slope, this 4. So we calculate this sloping length like this. Sorry, horizontal length like this. B1 is the distance between the piles, and they calculate this simple K. 3.3 is obtained from the table, negative because it is upward. They calculated this correction, apply this correction again, and do this. And again, do the same for downstream and for the same for the intermediate. Just for downstream, the difference would be for intermediate, we have to use this graph again. For downstream, just we have to use this graph. In case we have to use this phi d and phi e values. For downstream, we know that phi c value is 0. Why? Because the exit gradient we are assuming, if I draw this is C, this is D, this is E. We are assuming the exit gradient is 0. So phi C is 0. So phi D and phi E we can simply just directly get from these graphs. No need for any no need for any B1 or B calculations or something. Just calculate 1 over alpha. On x-axis this 1 over alpha and check these phi values. So any issue in this?
No answer.
All right. Should we? So this was all for Bharat portion. Should we end? If you want, we can have. Uh, sir, actually, sir, Noor's topics are quite easy. I can send the solve problem from for those. So they are quite simple. There are, if there is any issue on those, you can contact me. I'll try to have another meeting. The difficult portion was this part. All right.
Okay, brother.
All right. So any issue?